Hi, I'll talk about a comparative analysis between ammonia-water absorption and vapor compression refrigeration systems. My name is Wellorzzon Novais and I work at SISEA laboratory at University of São Paulo. Refrigeration systems are broadly used in food and drug conservation and in air conditioning. Commercial buildings demand up to 80% of total electrical power just for powering air conditioning based on conventional vapor compression refrigeration systems, called here just as VCRS. This contributes to reach peaks on the electrical distribution network that could cause an unstable condition. Implementing absorption refrigeration systems producing cooling effects driven by thermal energy could decrease this power consumption. Here we will treat absorption refrigeration systems just as ARS. Many references found in open literature analyzed the thermodynamic models of ARS, as shown in this table. Different working fluid mixtures or the integrations with VCRS or other systems were studied. However, these articles do not focus on a direct comparison between absorption and vapor compression cooling systems, which means using the same operation conditions for both and with the same refrigerant fluid. Thus, the current study aims to simulate and compare two different types of refrigeration technologies: single-stage ammonia-water absorption refrigeration cycle and vapor compression refrigeration cycle working with R134A and R717. This last is also called anhydrous ammonia, or just ammonia, and is the same refrigerant fluid of ARS. Thermodynamic simulation was carried out by using the engineering equation solver software. A thermodynamic model of ARS and VCRS were developed, focusing on evaluating heat transfer rates of the main devices, coefficients of performance, and specific areas of evaporator and condenser. From now on, I will talk about the details of each system. These are the systems in general. Both have subsystems in orange, coupled with evaporator and condenser to transfer heat. They were set to work within specific conditions to be simulated. Focusing on ARS, we can see here the mass fraction were set to be constant across the lines with the same colors. The heat exchangers are assumed with 80% of thermal effectivity, the pump with 85% of isentropic efficiency, and the expansion valve is assumed isenthalpic. Pressure drops and heat losses were neglected. This table shows the boundary conditions in the inlet or outlet flows of some devices for absorption refrigeration system, or ARS. The global heat transfer coefficients were 2.1 kilowatts per square meter Kelvin for condenser and rectifier and 1.9 for evaporator. The COP, coefficient of performance, was determined by equation 1. This in red is the refrigeration thermal load, that is equal to 15 kilowatts, and this is the heat transfer rate for generator. The specific areas of condenser with rectifier or evaporator were calculated according to the equation 2. This is the heat exchanger area of the device, which means the condenser with rectifier or the evaporator, and this is again the thermal load that I told you earlier. For the VCRS, the compressor was assumed with 85% of isentropic efficiency and the expansion valve is assumed isenthalpic. Pressure drops and heat losses were neglected. This table shows the boundary conditions in the inlet or outlet flows of some devices for VCRS. The global heat transfer coefficients for condenser or evaporator is shown in the table below. The values for R134A are lower than those for R717, according to Brazil 2017. The COP coefficient of performance was determined by equation 3. This in red is the refrigeration thermology again, and this one is the compressor power required to drive the system. The specific areas of condenser or evaporator were calculated according to the equation 2 already mentioned. The results for absorption refrigeration system with different evaporator temperature is shown in this figure. As the evaporator temperature decreases, the generator and absorber heat transfer rates increases, while the values for condenser and rectifier remain constant. The COP has lowered from around 0.6 to 0.4. The results for vapor compression refrigeration system with different evaporator temperature is shown here. As the evaporator temperature decreases, the compressor power and condenser heat transfer rate increases for both systems. That is to say, for those using R134A or R717. The COP decreased from around 6.8 to 2.6 for R134A and from 7.1 to 2.8 for R717. Analyzing the graphs together in number, the values increased more in ARS than those of driving power and condenser heat transfer rate for VCRS. The COP has very different values and VCRS has the best COP. These are the specific areas calculated for ARS, and it can be seen they remain almost constant as the evaporator temperature decreases. The specific areas for VCRS are higher for R134A because global heat transfer rates were lower for this refrigerant. Looking for the three graphs, the VCRS with R717 has a smaller heat exchange area. Since the refrigeration thermology are the same for all the simulated systems, and the condenser heat transfer rate for VCRS is lower than for ARS. For the conclusions, this proposed investigation was a great tool to verify which system has more benefits in different situations, such as a lower evaporator temperature. A thermodynamic simulation of ARS and VCRS were done, showing VCRS has the higher COP and needs less input energy than ARS. However, ARS can be used in places where there is no electrical power or even use heat waste to drive a refrigeration system. For the acknowledgements, me and the other authors want to thank CAPES, PAPESP, and Consciências to finance this research. These are the references used in this presentation, and thank you.